Okay, great. So this we use absolute value so that LD, the dispersion length, is always positive. The dispersion length is always positive. The dispersion itself could be negative and positive, right? K naught double prime could be positive or could be negative, meaning that higher frequency can be propagated slower, higher frequency could be propagated faster, right? But in the end, they will broaden, the dispersion will broaden no matter whether the K naught double prime is positive or not. And then last class, we also learned the nonlinear length is 1 over gamma p, right? Nonlinear length is 1 over gamma p. Nonlinear length is 1 over gamma p. So last class, we learned that we're able to find T naught. We're able to find T naught and P so that LD equals L nonlinear length at 500 kilometer, right? That's what we learned from the last class. Today we will still give different different scenarios, right? We will still give different scenarios looking at how would the nonlinear length and the dispersion length, play a role in whether my transmission is dispersion dominate or nonlinear dominate, right? So in this case, let's look at, we want to find dispersion length and the nonlinear length with this T naught as 1 picosecond, and then T naught and P naught is 10 milliwatt, right? I'm sorry, 10 watt. Right? So what would be the P naught is 10 watt and the T naught is 1 picosecond, right? So let's just write down the equation. So this will be LD, right, is T naught squared divided by K naught double prime, absolute value. We use the previous examples, previous number, that's the 20 picosecond, right? So we have K naught double prime is 20 picosecond per square per kilometer. Let me write this way, it's the per kilometer. Right? Okay. We use the same, right? And the gamma is 2 inverse watt and the inverse kilometer. Right? Gamma is 2 inverse watt and inverse kilometer. So this LD is going to be 1 T naught. So in this case, the T naught is 1 picosecond, right? 1 picosecond square over 20 picosecond square over kilometer. So this would be 0.05 kilometer, right? So this dispersion is 0.05 kilometer, meaning that if I have shorter than 0.05, the dispersion won't play an important role. Then we calculate the nonlinear length. The nonlinear length will be 1 over gamma, and power this P naught, right? How much is gamma? Gamma is 2 inverse watt, inverse kilometer. And the P naught is 10 watt, right? So it is again, 0.05 kilometer. Right? 0.05 kilometer. So that would be altogether is the dispersion length and the nonlinear length. Right? Okay, so in this case, right? In this case, dispersive and nonlinear effects, right, need to be included. need to be included if the fiber is longer than 50 meters, right? So for example, if I only have 5 meters, then my pulse propagate in this case will almost no change, right? We don't need to talk about dispersion effect and nonlinear effect in this case. We don't need to talk about dispersion effect and nonlinear effect. Okay, so we have several other scenarios, right? In the case, so those are the dispersion effect and LD and NL, they're the same, but let's in the case L is much less than LD. L is approximately equal to L nonlinear length, right? The pulse evolution in fiber is governed by nonlinear effect. So in this case, because L is way less than LD, right? It's much less than LD. So this will be, we should the pulse propagation will be dominated by nonlinear effect. The pulse evolution in fiber is governed by nonlinear effect, right? So it is all by nonlinear effect. So let's calculate it. So my LD over L and L. First, we need to, I'm sorry. So the L is way less than this. This is this, right? So, okay, so that's good. So LD over DNL. So LD, right? So it should be LD should be way larger than 1, right? Way larger than 1. So let's say what is LD? LD is T naught square over K naught double prime. So it's T naught square over K naught double prime, absolute value. And what is nonlinear length is 1 over gamma P. So it's gamma P, right? 1 over gamma P in the denominator, meaning that it flipped up at the gamma P, right? So in order to do that, in the case that we have the same parameter, right? So T naught is 1 picosecond, gamma is 2 inverse watt. I shouldn't have a inverse watt, inverse kilometer, and the P is power is 10 watt, right? Power is do I have 1 picosecond with kilometer? No. Let me look at the power. So let me look at the power. So in this case, K naught double prime is can you be able to see it? Yes. So 20 picosecond square over kilometer, right? So with that, can you actually calculate how much is the power? So use this relationship. You find out how much is the power, what the power should be way equal to what number. So just speak out once you have a number.
Is it 10 watts?
How much is it?
10 watts?
10 watts. I think there's some your unit. There's difference in your unit.
Okay.
10 watts per kilometer, or 10 watts kilometer squared.
How much is it? Can you, so the number 10 is correct, but the unit is wrong. So let's do it together, right? So P naught should be K naught double prime, and then divide by T naught square gamma, right? Gamma. I think this is 20 picosecond square over kilometer. And then this T naught is 1 picosecond square, and gamma is 2 watt. Yeah, you're right. 2 watt. Yeah, okay. Yeah, I apologize. I think you got this correct in the first try. Yeah, it's the 2 inverse watt inverse kilometer, right? So the result is 10 watt. Is 10 watt. So this P naught should be way larger than 10 watt. Thank you. You got it right. So we need to be the P naught needs to be the 10 greater than 10 watt in order to have this the pulse evolution in the fiber is governed by the nonlinear effect, right? It's dominate. Once you actually so let's see what is the LD. You can calculate the LNL and LD, right? So you can calculate the LD and one and NL in this case. So let's do it, right? So in this case, let's say because it's dominated by this L and L, right? L and L is 1 over gamma P, right? 1 over gamma P. So this is, for example, it's the power needs to be greater than 10 watt. Let's assume this is 10 watt. 10 watt times gamma is 2 inverse watt inverse kilometer, right? It's the, again, this is 0.05 kilometer, right? Okay, great. Okay, now let's see. So this needs to be way larger than 10 watt. So that now it is dominated by nonlinear effect, right? So now let's do the second case, which is the LD is way less than in the case. So let me see. In this case, yeah. In the case L is way less than nonlinear length, L is approximately in dispersion. So it's the opposite, it's the flipped, right? Flipped case. And in the case of this, L is way less than nonlinear length, L is approximately equal to LD. The pulse evolution is governed by dispersion effect and this nonlinearity, right? So this nonlinear effect, yeah, effects play a relatively minor role. Play a relatively minor role, right? Okay, so it's the flipped side, right? So in this case, our LD over LNL, which is still the same, T naught square times gamma P over K naught double prime absolute value. This time, LN is way larger than L. LD is approximately equal to L. So this time we will have way less than 1. Way less than 1, right? Okay, so we'll do the same. We'll do the same number, right? We'll do the same number. So in this time, this power should be way less than K naught double prime divided by T naught square gamma. It's the same number, right? 20 picosecond square over kilometer divided by 1 picosecond square, and then times 2 inverse watt inverse kilometer, and then we know it's the 10 watt, right? So P needs to be way less than 10 watt in order to have the pulse evolution is governed by the dispersion effect. Right? Okay, so in this case, let's calculate what is LD, right? Let's say what is LD? LD in this case is T naught square over K naught double prime, which is 1 picosecond square over 20 picosecond square over kilometer. So it's 0.05 kilometer, right? 0.05 kilometer. So, and then our nonlinear effect, let me borrow some space. Let me actually use the space here. Right? So in this case, our nonlinear length is 1 over gamma P. So since P is going to be way less than 10 watt, so it will be greater, much greater than the 1 over 2 gamma, 1 over 2 watt inverse kilometer inverse times 10 watt, right? So this value would be 0.05 kilometer. So L nonlinear length would be way greater than 0.05 kilometer. So in this case, the LD is 0.05. Nonlinear length is way larger than 0.05. Right? So LD is 0.05. Nonlinear length is way larger than 0.05. So that means my effect, my propagation is governed by dispersion effect, right? Because when we actually below 0.05, there's probably no dispersion, but once after 0.05, dispersion effect dominates, right? Dispersion effect dominates. So you would ask, so we have this case, the case of, right? The case of, this is nonlinear dominate. This is dispersion dominate, right? So depending on the power, right? Because the dispersion effect does not depend on the power. Dispersion effect only depends on the spectral width, right? Spectral width, how much is the dispersion, but the nonlinear effect dominates by the, so this is the dispersion effect dominated by what? By this pulse width and how much the dispersion in the optical fiber. The nonlinear effect dominated by this nonlinear coefficient gamma and the power, right? This power. So I use the power P or P naught. So it just, but they're the same, right? The P or P naught. Okay. So depending on the power, so power very large, if power is way greater than 10 watts, then nonlinear lens is very small, so it's dominated by the nonlinear effect. However, if the power is very small, then this nonlinear lens is going to be very big, so that this pulse evolution is dominated by this dispersion effect. Okay. Okay. Any questions? Any questions on the here? Any questions here?
No, sir.
Okay, great. Thank you. So in between, then actually the problem is what's in between, right? So in between, for example, when pump power, right? Power is I use P naught and P, but they're literally the same thing. In between, when the pulse is dominated by both dispersion and the nonlinear effect. In between, the pulse is dominated by both dispersion and nonlinear effect, right? So let's write the equation. Let me write this equation again, right? It's actually a very handy, equation. So it's I partial derivative with partial zeta, right? So equals to SGN K naught double prime and half of the partial U partial tau, right? Minus N square exponential negative alpha Z U absolute value U. So I now have this normalized, right? There was a dispersion length here, so I divide by dispersion length, right? Now here is remember there's a gamma P here, right? If you check your previous equation, there's gamma P here. So I actually the scaling property. I just make it into a, so change the scale, right? Zeta is Z over LD, right? I normalize, it was an LD there, so divide by LD. And then my tau is T over T naught. So this time is now scaled by T naught, right? Tau is scaled by T naught. And then my U is A divided by square root of P, right? So my U is A divided by square root of P. Okay. And then what is this N? N actually has an gamma P. So I use N square as LD over NL, which is gamma P T naught square over K naught double prime absolute value, right? Absolute value. So it's all normalized. It used to have the gamma P in here, right? Then I divide by LD and put all this LD and the gamma P T naught square K naught double prime in here. So replaced by this N square. And we will use this N square later on, right? Use this N square later on. So this is the nonlinear Schrodinger equation, right? So so normalized. So this is the normalized normalized NLS equation, right? Equation. Normalized nonlinear Schrodinger equation, right? Previously, it's the whole thing, but now it's normalized. It's easy to see, right? So now let's see. In the case n equal to 1, what does it mean? When n equals 1, that means LD and L, they are the same, right? So in the case, so the first case, if I have T naught is 1 picosecond, right? T naught is 1 picosecond. We use the, let's say, gamma and then K naught. So we can find out, so let's say gamma is 1 picosecond, right? It's equal to 0. So P naught, right? P naught. How much is the P naught? It's the K naught double prime absolute value divided by gamma and the T naught square, right? Let me borrow some space here. Right? Okay, so this is 20 picosecond square over kilometer divided by 2 inverse watt inverse kilometer. T naught is 1 picosecond square, right? 1 picosecond square. Okay, so in this case, it is if it's 1 picosecond, we got 1 picosecond to it is this is inverse kilometer, right? Inverse kilometer. So this is 10 watt, right? It's the 10 watt. Did I calculate correct? I think so, right? Divided by 2. Okay. So now let's say in the case of 2, T naught is 10 picosecond, right? Let's say it's 10 picosecond. So if it's 10 picosecond, then my P naught is K naught double prime and gamma T naught square, right? P gamma T naught, yeah, okay. So this is absolute value, and then still 20 picosecond per kilometer square over 2 inverse watt inverse kilometer. But since my T naught is 10 picosecond, so it's 100 picosecond square, right? 100 picosecond square. So in this case, it is the 0.1 watt, right? So it is 0.1 watt. It's the 0.1 watt. Yeah. Okay. Okay. So if I have n equals 0, right? N equal to 0, that means the dispersion length and the nonlinear length relatively the same scale. They play equal important role. So if my T naught is 1 picosecond, my P naught will be something like 10 watt. However, if my T naught is 10 picosecond, then my pump power is 0.1 watt. It's the 0.1 watt, right? It's the 0.1 watt. So it means that if I increase my time domain, right? If I not increase my time domain, I increase the pulse width. So this is very narrow, right? This is in time. This is very broad in time. Very broad in time. So then which one will have Which one will have less dispersion effect? The first one will have less dispersion, or the second one will have less dispersion?
The first one. Oh, the second one, sorry.
Yeah, the second one, right? The second one has less dispersion because if you take the Fourier transform, you have in frequency domain, this going to be very broad in frequency, right? And here it's going to be very narrow, omega. So it has less dispersion effect, right? So for the pump power, which one has less nonlinear effect? Of course, the second one, right? Second one has less nonlinear effect because it's small power. So that means if I actually have less dispersion effect, then we should have less nonlinear effect, right? So that will, in this case, in the case of n equals to 1, they are almost the same. They are almost in the same important rule, right? The same important rule. Okay. Questions? So those will be actually very likely will be in the exam. So try to make sure you understand the material, right? Try to sure you understand the material. So and what is this n, right? N actually governs the relative and governs the relative importance of the nonlinearity and the importance of the nonlinearity and the dispersion effect, right? Okay, so if n greater way less than 1, this will be dispersion dominates, right? So if n much larger than 1, it's nonlinear dominates, right? So when n is I still have space, n approximately equal to 1, both play an equally important role, right? Play an equally important role, right? So both play an equally important role. Okay, so we also want to define a sign, right? So there's if the k naught double prime is greater than 0, it's called normal dispersion. Normal dispersion. K naught double prime is less than 0, it's called anomalous. M-A-L-O-U-S dispersion. Anomalous. Let me write it more clear. Dispersion. Anomalous dispersion. So we have normal dispersion and anomalous dispersion. Normal dispersion and anomalous dispersion. Okay. Okay, so now let's look at how to solve this equation, right? How to solve this equation. So let's write a normalized, so NLS. So in order to solve this, it's actually quite complicated equation, right? So next step, we will solve this NLS is a nonlinear partial differential equation. Is a nonlinear PDE, right? So NLS is a nonlinear PDE. Sorry, I missed a square here, right? And I missed a square here. So if I don't have this square term, then this would be a linear equation, right? That's what we learned from the signal system, right? So, but this is nonlinear equation, and although you could do some analytical solution, but usually a numerical approach is therefore often necessary, right? A numerical approach is often necessary. Although some special case you could solve it by analytical method, but general case you want to use it numerical approach. So we will use so-called split step Fourier method. So we will use split step Fourier method. So you probably from this name, you can guess that you need to use Fourier transform, right? Okay, so let's rewrite this equation. Let's do a simple example that there is no loss, right? There's no loss. Let's for the case of no loss, right? For the example that we have no loss. So the partial u partial z, right? So I'm actually, instead of zeta, I'm going back to the z. So it's we'll just make a simple equation, right? So this will be I. I'll move the I to the right hand side. So it's I SGN. It's the sign, right? SGN divided by 2 partial u partial tau, right? Partial u partial tau, and then it's the second derivative. Sorry, I take it wrong. I have quite some typo in this equation. So this is partial u. This is partial u partial tau square, right? So that's the typo. So please, this is the right second derivative. Okay. Okay, then you have u. So it's actually nonlinear, right? Even if you remove the u square, this is actually nonlinear too. Minus n square, right? So this dominates whether the nonlinearity or dispersion, the effect is dominating, right? U square u. U square u. Okay. So now let's separate out. This is the dispersion effect, right? This is dispersion effect. This is nonlinear effect, right? So I'm going to further write as the operator, right? Dispersion operator and the nonlinear operator, right? Dispersion operator and the nonlinear operator. So let me write as partial u partial z equal to this dispersion operator and the nonlinear operator, right? So this is the dispersion operator. I use the hat to indicate this operator, right? So this dispersion is the differential operator for dispersion, right? So this is the, yeah. It's the second derivative, right? So it's the second derivative and the differential operator for dispersion. Right? So this D is the differential operator for dispersion. And then N, this nonlinear is the nonlinear operator. For nonlinearity. Right? So this is the nonlinear operator, this is dispersion operator. So what it is that the dispersion operator is negative I SGN, it's the sine k naught double prime over 2 partial tau second derivative, right? And this nonlinear operator is the I, right? So, so if we move this, that should be the positive. There should be an I. Yeah. Today is not a good day for me to write the equation. So, so if I have the I moved I to the right hand side, there should be a negative I here. It was a negative, so it's positive I. So the nonlinear operator is I n square u absolute value square. Right? Because that's the operator operate on this u. So I have I n square u, I n square u. Right? So in general, D and N operate, act together. Okay, so in general, D and N act together, right? Okay. And the way how you solve this, usually you have a step, right? So you have a step. So this will be solved in each of the step. We solve this dispersion in the half of step here, half of step there. And then we calculate the nonlinear operator in middle. So in other words, you have small sections. You have small sections. When the pulse propagating small section, we need to include, because they play a role in, together, right? They play a role together, but we really cannot, it's really difficult to solve this together. So in each small step, we calculate the D by 2 small half step, and then we calculate the nonlinearity by small steps, right? Remember, we can solve the dispersion by small step, right? And then we can solve the nonlinearity in small step too, right? So in the end, we take small steps. We include the nonlinearity and the dispersion. And then we take small steps in order to make the propagation, right? So in the previous case, right? In the previous case, in the lab session 2 and 3, we only make one step because we can solve this equation by using one step. And for the nonlinear effect, we can also solve by one step too. However, when they play a role together, we cannot by one step. They play a role, continuously together. So we have to make small step. Each of these small step, we need to take into consideration of the both effect together. So that's how you actually include the dispersion, half step, and then nonlinearity, then dispersion, half step. There are some theory behind, and the scope of this theory is beyond this theory is beyond the scope of our class. So we'll just use this, half dispersion, nonlinearity, and then half dispersion. Okay, so that's all for my lecture piece. Do we have any questions? Any, I know there's some of the quite some materials. I hope we have in person. That will we probably can have better interaction. Unfortunately, we have the online version. So do you have any questions? Okay, so I have some slides. Let me share my screen. I have some slides. I will share my screen. So hold on, let me make it clear. Okay, so let me share my screen. This is the piece. Okay, no. Okay, so let me share my screen. Share my screen, hold on. Okay. Okay, let me share my screen. Okay, can you all see my screen?
Yes.
Yes.
Can you see my screen?
Yes.
Okay, thank you. Okay, so this is the pulse propagation, right? So again, I grabbed some of this, some picture from the published results, which will better illustrate the concept, right? Remember, in the dispersion, when we studied dispersion, we found out that in spectral domain, it doesn't change, right? In dispersion effect, in spectral domain, it will add exponential I k naught double prime over 2 omega square z. But now it adds in the time domain. It adds the time domain as the exponential n u square, right? So this is the propagation. The first row is the original, so there is no phase variation. But once it propagates some distance, this is time domain, this is spectral domain, right? Time domain, spectral domain. For the third column, let's don't look at the third column yet. So for this piece is in the time domain, you can see for the nonlinear effect, in time domain, it doesn't change the shape. It only changes the phase, right? Because in the in the nonlinear effect, we will only looking at the exponential I gamma u square z, right? So this is the exponential I gamma u square z, right? Depending on the how much is the z. And now if we add more distance, so if we add more distance, you can see it changes more, right, by phase. So this is the phase. But in the spectral domain, it not only changed the phase, but also changed the shape, right? It changed the shape in the spectral domain. So the nonlinearity, it does not change the shape or amplitude in the time domain. It changes both the shape and phase in the spectral domain. But in the dispersion effect, it does not change the shape in the spectral domain, right? So they are the corresponding parts, right? Dispersion and nonlinearity. Okay, so now let's look at the third column. The third column is the time and look at the local frequency. In other words, once you add some phase, you actually modulate the frequency, right? Modulate the frequency. So it changed the frequency a little bit. Right? So it adds the phase modulation in the time domain. Correspondingly, it changed the local frequency, right? Local frequency. So it is more like a chirp in the time domain, right? Chirp in the time domain. Okay. Okay, great. That's please feel free to interrupt me if you have questions, right? Please feel free to interrupt me if you have questions. Okay, so I collect for the same, thing, just like what we studied dispersion effect. I also collect some of the research article, and those are the quite some fundamental research, right? It is not the research nowadays. So you can see the year is 1981. So those nonlinearity and dispersion is the hot topic of research field in 1980s, right? And some of the 90s. So those are old days, right? Okay, so we have mode-lock laser, laser beam, and so quite other device. That's how you measure it. But the key point is passing through this single mode optical fiber. So single mode meaning that a mode electromagnetic wave, there's only one pattern, electromagnetic pattern. So, and then this is the optical fiber, and we will look at this wave propagation in the optical fiber. And you can see that this is in the time domain. It's excuse me. So in this time domain, it makes the pulse in a square shape. So this is the calculated pulse shape via distance in meters. So it's 10 meter, 20 meter, 30 meter, 40 meter, right? Remember, the dispersion effect only broadens the pulse still in the Gaussian shape. But however, nonlinearity will actually operate in different phase in time domain, right? So due to the changes in the nonlinearity and the dispersion, they act together. It will actually have some special effect and make a square-shaped pulse. So that's the nonlinear pulse propagation, right? Nonlinear pulse with the group velocity dispersion. That's the with the dispersion. Okay, so next we'll look at the evolution of pulse shape and optical spectrum, right? So this in time domain, did you see it's T minus T naught, right? T minus T naught. It's the nu. This is the angular frequency, right? It's a frequency, sorry. Nu usually it's represent the frequency. Frequency minus frequency nu naught, that's the center frequency. It also normalized by T naught. So it's the normalized spectrum, right? And the Z over LD, that's the dispersion length, right? That's the dispersion length. Also, we propagate the dispersion length we can see that this is the one dispersion length, two dispersion lengths, 3, 4, right? That's similar to what we plot previously, right? But now in an evolution way, right? So when you see in this case, it's for 5LD, and they are n is 1, so dispersion and the nonlinearity almost they play equal important role, right? Almost play an equal important role, but still broaden, right? So it's the altogether it broaden the pulse.
Dr. Who?
Yes,
Sorry, I had a question about the second figure.
great. Are you talking
So-
about this figure or that figure? It's the
Uh,
slide number 4.
The one we were just on.
Okay, this one.
Yeah, so it looks like, so the second one is, are both of these with nonlinear and dispersion effects?
That's correct.
Okay, and, okay, that's it.
Yeah, so yes, so thanks for asking. So if we will only have this dispersion effect, you would think, the pulse is broadened, the pulse time domain is broadened, the spectral domain didn't broaden much, right? That means I have a lot of phase actually in it, right? It has the phase variation in it, right? So in this case, we will we have a lot of phase in it. So the time domain it will broaden a lot, right? Okay, great. Thanks for asking. Okay, now let's look at the other case. So the first case has the beta 2 greater than 0. Second case, beta 2 is less than 0, right? So in other words, the nonlinearity play a role always one unique way, right? They always add the phase I gamma U square. But dispersion can be kind of opposite, right? Dispersion can be positive dispersion, normal dispersion, or anomalous dispersion, right? So in this case, you can see that the broadening is not a lot compared to the previous case, right? So the previous case broadening a lot. The second case, it does not broaden a lot. The reason is that the dispersion and the nonlinearity can play a role constructively together or destructively together. So in the case beta 2 less than 0 or k naught double prime is less than 0, they kind of cancel each other, right? They play a role. Remember that dispersion will add the phase in the spectral, nonlinearity add the phase in the time domain. But in the end, if they have the different sign, if the k naught double prime is less than 0, they could cancel each other. They could cancel each other. This effect is very similar to the pre-tripped effect, right? So in other words, before propagation, if we have C, the tripped factor C and the k naught double prime, they have different sign, that you can end up compress the pulse, right? So this is actually very similar in the sense that my k naught double prime and the nonlinearity, they act destructively together, so they cancel the effect together. They almost preserve the shape. It's actually quite interesting, right? Okay, so please interrupt me if you have question. Let's move on. So that is the picture we can show. This is the broadening, right? So the broadening, if the so n equal to 0 is no dispersion effect. I'm sorry, no nonlinear effect. If its nonlinear effect is included, beta 2 or k naught double prime is less than 0 has less broadening, right? So this is k n equal to 0 is absence of self-phase modulation. That means nonlinearity. So n equal to 0 is the no nonlinearity, right? No nonlinearity. So So in that case of n equal to 0, no nonlinearity. And once we add the nonlinearity back, depending on different sign of the dispersion, k naught double prime, if the k naught double prime is less than 0, they act destructively, you have less broadening, right? This effect is very similar to the pre-chirp propagation, right? Okay, great. Okay. Okay, so now one would ask, right? One would ask, can they actually compensate? Can they actually just totally cancel each other, right? So can you actually have a pulse? It propagates with the preserved shape, right? The dispersion and the nonlinearity, they preserve the shape because they can cancel each other. So this is called soliton propagation. So it is a self-reinforcing solitary wave. It is caused by a cancellation of nonlinear and dispersive effect. It was first observed in John Scott Russell at Union Canal in 1834, right? It's a long ago. So there, he saw a horse dragged a boat, and then it caused the wave. And then the wave in the water, it does not change the shape in a long distance. Of course, the amplitude does decrease, right? So in 1995, the scientists having a soliton conference, and they want to reproduce the solitary wave, soliton propagation. So they used a boat, they drive a wave, and then they can observe this wave preserve the shape in a very long distance, So this is called soliton propagation due to the cancellation of the nonlinearity and dispersion effect. Okay. Okay, so here's the soliton propagation, and you can have n equal to 1, you can have n equal to 2, n equal to 3. What is n? N is t naught double prime, t naught double prime gamma p over k naught double prime. I'm sorry. It's the t naught square, n is the t naught square times gamma p over k naught double prime, right? So if you have n equal to 1, then you will preserve the shape. But if you have n equal to 3, the pulse will propagate, and they will at the beginning, nonlinearity play a very important role. So it compresses the pulse. Once it compresses the pulse, you have very broad spectrum, right? You have very broad spectrum because you compress the pulse, you get broad spectrum. Once you have broad spectrum, dispersion play a more important role. It will come back and it become the two pulse, right? It will make the pulse broadening in time domain. It makes two pulse, and then in the end, it will come back to the very sharp pulse, compress the pulse again, and then in this case, it will come back with the original pulse shape. So you can see this is soliton propagation where n equal to 3. They break the pulse into two pieces, and then we have the original pulse again, right? So it's the soliton propagation with n equal to 3. Okay. Then we can see this is the contour plot, right? This is contour plot. You can see the dark represent the high amplitude. So you can see very high power here, and then break into 2 pulses, and break into 3 pulses, and come back to the original one. This is the corresponding evolution in the spectral domain. This is corresponding evolution in spectral domain. Right? Okay. And this is another example. So this is then let's directly look at the experiments. So this is experimental results, right? Experimental result. This is the laser output. So in this column is the time domain. This row is in time domain. This row is in the spectral domain. The picture in the box is the laser output. Excuse me. When the power is very small, because it's really hard to look at the pulse shape in the optical fiber. So we want to look at the end of the propagation, right? So at the end of propagation, if the pump power is very low, it is dominated by dispersion effect, right? If the pump power is very low, it is dominated by dispersion effect. So, and at they're slightly broadening compared to the original laser pulse. But if you increase the pulse power, you get the original pulse back, right? You get original pulse back. That is because I'm operating at n equal to 1 soliton propagation, right? N equal to 1 soliton propagation. And now I further boost up the pump, the laser power. It will get the narrow and then 3-step and then very broad pedestal, right? So it demonstrates that although I'm not able to look at in the middle, right? But by changing the pump power at the end, I can look at the original pulse or the compressed pulse or 2 or 3 pulse together, right? So that's what they observed in experiment, that low power dispersion dominate, the n equal to 1, it's play an equally important role. And now with high order soliton with increased pump power, right? Power, so n equal to higher number. So that will give us the more demonstration of this soliton propagation. Okay, great. So again, this is the modeling, right? Simulation. We're going to do similar stuff in our lab session also. So you propagate, you split into 2 pulses, and then come back to 1 pulse, come back to the original pulse, right? Okay, so you can see that it's the similar experiment. This is the fiber output. It's really hard to get in the fiber, right? In this fiber, but rather we will increase the pump power to see if what happened at the end of the power. So you can see, right, when you boost up the pump power, you can tell that it's the 3 peak, right? 3 peak. This A represent N. Actually, it's actually N in our case. So you could roughly tell that it's the 3 pulse, right? It's the 3 pulse. It is done in 1983, so it's not a very very nice picture, but at that time it's already very good results. Okay, so this is the calculated pulse. You can see it's very narrow, right? Very narrow, and that's the experiment, right? So you can see this is the input pulse, right? Input pulse, and then it's n equal to 3. It can be compressed if it's high order soliton n, right? And it's larger, the pump power is great. It's larger and larger. You can compress narrower, right? Further narrow pulse. Okay, so that means in this case, I can use this nonlinearity and dispersion effect. They play together, so we will compress the pulse. Yeah. Okay, so that's it for today's class. We will conclude here, and next class we will go to the lab session. We'll study how to solve this nonlinear Schrödinger equation. I have another announcement I need to make. That is that Monday next week, I need to attend a meeting. So we will again move the class to Wednesday and Friday. If you have any conflict, please let me know. I'll try to make some arrangement. But Monday's class is canceled. I need to attend a meeting. There is a faculty candidate here, so there's some meeting I need to participate. So we will move our Monday's class to Friday. Thanks for your flexibility, accommodating our class. Any questions regarding our class and question for today's class lesson?
Doctor Who?
Yes.
We don't have school next Friday.
Oh, yes, thank you. That's correct. So let's actually move the class to the Friday next week. Yeah, thanks for reminding me. That's the Easter holiday. Let's move to the 9th. Let's move
Doctor
to
Who.
yes.
The 9th is my thesis presentation.
Oh, yes. Thank you.
Sorry.
No, that's fine. Thanks for 9th. How about 16? Any conflict on 16th? Yeah. Okay, so it looks like 16 should be okay. So later on, I will try to write another email. So let's tentatively make it into 16, right? Tentatively make it into 16. It looks like I have another meeting, so 23 should be there. But let's, I will send out another email. So if you cannot make it, please let me know. Yeah, have any concern? I'll try to make arrangements so we can accommodate everybody. Yeah. So thanks for being flexible. I know we changed quite a lot class, and I know you guys being flexible. I really appreciate. And this is a difficult, time, right? So learning online is relatively difficult compared to in person, but let's work together, right? Let's work together. Okay, so I think that's it. I'll see you Wednesday next week. We'll have a lab session. And just a friendly reminder, homework 3 lab session is due today, by the end of today. Okay. So if there's no further question, I'll see you Wednesday next week. Okay, bye.
Thank you.
Bye.